All right. Good morning, good afternoon, or good evening, everyone. We are back for our final lecture of Organic 2 this semester. This is lecture number 30. This is the end. And in this lecture, we're going to start looking at some more reactions of 1,3-dicarbonyl compounds. Here we're going to focus on what is called the acetic ester synthesis, and the overall process will turn ethyl acetoacetate, or these types of derivatives, into a new derivative where we've actually completely lost this entire ester portion. And along the way, we also have introduced a new R group. So the reactions performed under basic conditions with sodium ethoxide and ethanol. So we can draw out the ethyl acetoacetate. We're going to have sodium ethoxide in solution, so it will go and deprotonate the most acidic proton, which is the proton that's in between the two carbonyls. Note that this other hydrogen that I'm drawing in red will have a much higher pKa because it's only stabilized one of the oxygens. And also keep in mind that if the ethoxide were to attack this ester, you'd make a tetrahedral intermediate that would only be able to collapse back to itself. So we're able to make the enolates as we have before. So these enolates, even though they are quite a bit more stable than your average enolate, and they don't react with things like esters, they are able to react with things like alkyl halides. So for this example, I'll draw an actual molecule. Let's say we're using ethyl bromide, and we can add this in, and we can control this with stoichiometry. So if we say one equivalent, we'll only get one equivalent out afterwards. So we'll do an SN2 reaction. We still have a reaction at carbon of the enolate. And we're going to make a new alkylated ethyl acetoacetate derivative. And if we still have a lot of extra base around, this may get deprotonated. We'll take this hydrogen. We'll re-enter this equilibrium. That should be pretty favorable given the pKa's of ethanol and the acetoacetate. So the reason we're able to control stoichiometry pretty well is because once we get to this more substituted enolate, it has a slower rate of alkylation. So we definitely, if we wanted to introduce two different R groups, we could add two equivalents of the alkyl halide. If we just want one alkylation, we can just put one. And then finally, we can do a water workup. This usually is probably better described as being something like ammonium chloride, just so that we know that we can have enough protons around to protonate our carbonyl. And we're able to successfully isolate the target compound that we see above. Now in the next step, we have a couple things that can happen, right? We have sodium hydroxide, and then we add carboxylic, we add an acid, and we see we lose CO2. So if we added sodium hydroxide to an ester, we know that this is going to hydrolyze that ester. So I'll show the hydrolysis product. Initially, we have a carboxylate. We still have this ester present. When we add acid, if we add our hydronium, this is now going to reprotonate this and actually make the carboxylic acid. So this is when things get a little bit more interesting. So I'm rotating around this bond, and I'm doing this because we're going to need to have it in this position to see the next mechanistic step occur. So somewhere along the way, we end up making a product that has all of this carbon dioxide lost. So there's a nice way to draw the mechanism for loss of carbon dioxide. Once we get to this carboxylic acid, if you heat it up enough, you can actually have the lone pair from this carbonyl that probably already is hydrogen bonding. Grabbing this hydrogen, this breaks the bond to the carbonyl, and we can have arrows that go all around in a circle, much like a pericyclic reaction we've seen before. This briefly gives us an enol intermediate that we know will be in favorable equilibrium through tautomerization. So these end up being fairly convenient building blocks because we can reliably alkylate them under fairly mild conditions. We don't need to use something like LDA. We can control installing one versus two different types of alkyl groups. And it provides a nice method for directly making different sort of ketone derivatives. So it's a few steps, but let's practice an example. So we think in the first stage we're going to add sodium methoxide and our first electrophile methyl iodide. So from the first step, we would end up simply alkylating the central carbon. So we'll go through the same deprotonation followed by alkylation. Then we're going to add in sodium methoxide and have ethyl bromide added in. So I'll write this step out. As I mentioned, we can now introduce a second equivalent. It'll still go to this central carbon because that's the most acidic. It has the most acidic hydrogen on it. And now we can make a compound that has both a methyl and an ethyl on this carbon. Now we're going to go through the process of sodium hydroxide in heat, or sodium hydroxide followed by H3O+. This gives us our carboxylic acid that now has two different groups. And now with extra heat added as well, we can draw the arrows going around in a circle, initially giving the enol. It now has two different groups on this same carbon. So now you can potentially see maybe a strategic advantage of this chemistry. If you wanted to try to make this compound from acetone, that'd be a very difficult thing to do. So if we try to use something like LDA, that's going to result in quite a bit of challenges. So LDA plus acetone followed by something like methyl iodide will be fine for making a ketone that has a single substituent on it. But then the second deprotonation with LDA, in addition of ethyl bromide, this would end up putting it on the opposite side because now it's less sterically hindered. So this method lets us introduce two different electrophiles sequentially to the exact same carbon. So these two methods are a bit orthogonal and can give you different types of products.